Properties of liquids. So intermolecular forces help explain structural features and properties of liquids. Surface tension is one property of a liquid that it helps explain. Molecules at the surface are pulled down and sideways, but not pulled up out of the surface. So in this picture you can see the red arrow of the surface atom being pulled in all of the directions. Now if we look at the atom in the middle of the liquid, it's really being pulled both up, sideways, and down. The molecules are pulled then into the liquid, which causes surface to tighten like an elastic film. Outside the container, liquids with strong intermolecular forces will bead. So if it wasn't in a beaker, if it was just falling from the sky, let's say like our rain, the water will bead up or form a sphere to minimize the surface area. So surface tension is the amount of energy required to stretch or increase the surface of a liquid by a unit area. The stronger your intermolecular force, the higher the surface tension. Capillary action is related to surface tension. It's the spontaneous rising in a tube due to the cohesive and adhesive forces. Cohesive is the intermolecular attraction between like molecules. So if we think about water, it's in a tube in picture A. Cohesive is the attraction between the water molecules. Adhesive is the attraction between unlike molecules, the attraction between the liquid and the tube. If the adhesive forces are stronger than cohesive, the contents are pulled up. So water water will magically, quote unquote, be pulled up the tube because the adhesive forces are stronger. In fact, we see a meniscus form at the very top because it's more attracted to the sides of the containers. Cohesive, if cohesive is stronger than adhesive, the contents are actually low. They won't really rise in the tube. Picture B is an example of mercury. And if we look at the very top of the liquid in the tube, it actually has a dome type appearance because the molecules are more attracted to themselves. Viscosity is the measure of a fluid's resistance to flow. The greater the viscosity, the slower the liquid flows. Viscosity usually decreases as temperature increases because you're giving the molecules more energy, so they're moving faster. So hot molasses flows much faster than cold molasses. That might also be the reason why people get served hot syrup at restaurants instead of cold syrup, because it helps the syrup flow. The stronger the intermolecular force, the higher the viscosities. Liquids with complex shapes also have a greater tendency to become entangled, which can contribute to higher viscosity. For example, glycerol. This is the geometry of glycerol, and we can see these little hooks that we have with our oxygen, and so they get entangled and they have a hard time flowing. The structure and properties of water. Water is a very unique substance because of the hydrogen bonding that exists. So if it didn't have hydrogen bonding, water would actually be a gas at room temperature. But because of the hydrogen bonding, it has special properties. One is that it's an excellent source or an excellent solvent for ionic compounds. So ionic compounds will dissolve in water. It has a high specific heat, so it can absorb a lot of heat before the temperature of the water actually increases, which is why it takes a while for our swimming pools to become warm in the summer or to not be cold in the summer. It also gives off a lot of heat even with a slight decrease in temperature. So in the wintertime, areas around lakes tend to be a little bit warmer because the water is releasing energy as it freezes. So it helps regulate climate near bodies of water. Water would also absorb some of the energy from the sun during a hot day, so it would feel cooler to us near the water because we're not absorbing that amount of energy. Its solid form is less dense than its liquid form. So in the picture we can see our ice cubes floating in our liquid water, but if we put solid benzene in liquid benzene, it would actually sink. So water is actually an extensive 3D network with hydrogen bonding occurring. So the picture, the red dotted lines would represent hydrogen bonding. So if we take the hydrogen bonding plus the actual bonds to hydrogen into account, oxygen has a tetrahedral shape. So it's highly ordered structure. So ice prevents the molecules from getting too close to each other. They're kind of limited to how close they can get because of the tetrahedral shape. When the intermolecular forces overcome, when we give them enough energy, some of the molecules, quote unquote, break away, but they'll become entrapped by the other cavities of the liquid structure. As a result, there's more molecules per unit in the liquid than there is in the ice. So the density of water is greater than the density of ice. At the same time, water expands as it's being heated, so then the density also decreases there. Alright, so now we're talking about solids, crystalline structures. Crystalline solid possesses rigid and long-range order. Its atoms, molecules, or ions occupy specific positions. The arrangement is such that the net attractive intermolecular forces are at their maximum. Amorphous solids lack that well-defined arrangement and long order, and we'll talk more about them later. A unit cell is the basic repeating structure of the unit of a crystalline solid. So in our picture, A would represent the unit cell, and each little corner would represent an atom, ion, or molecule. If we were to repeat that pattern over and over again, we get the lattice structure. There are 7 types of unit cells. The simple cubic has all sides and all angles that are equal. It's in the simplest form. Any of the unit cells, when repeated in space in all 3 dimensions, form the lattice structure which is the characteristic of a crystalline solid. How do our atoms actually arrange themselves in the lattice? So the way spheres are arranged in the layers determines what type of unit cell that we have. So in this picture, this is the simple cubic. Each sphere in this arrangement has a coordination number of 6 because it has 6 immediate neighbors. The coordination number is the number of atoms or ions surrounding an atom or ion in a crystal lattice. The value gives us the measure of how tightly packed the spheres are. The higher the coordination number, the more tightly packed it is. There are 3 different ways of packing. You can have a simple cubic cell, a body-centered cell, or a face-centered cubic cell. So a simple cubic, you only have atoms at the corner. A body center, you have one in the center and then on the corners. And in a face center, you have one on each of the faces and then in the corners. The bodied center cubic arrangement differs from the simple cubic in that the second layer of spheres fits into the depressions of the first layer. The coordination number then is 8. Every unit cell is adjacent to other unit cells, so most atoms are actually being shared by all the neighboring cells. So when we talk about a corner atom, we're really only talking about 1/8 of that atom. So the corners would be 1/8 of an atom. The edge, being shared by 4 unit cells, would be 1/4. And the body would be 1 because it's only in that one cube. So a simple cubic, only having them at the corners, would actually be 1 sphere. Bodied center would be 2 spheres, 1 from the corner, 1 from the center. Face center cubic would be 4 spheres, 1 from the corner, and then 3 from the faces, because the face is going to split it in half. Closest packing. So there is more empty space in the simple cubic and body center cubic cells than the face centered. Closest packing is the most efficient arrangement of spheres. So when we arrange them, they could have an ABA arrangement called hexagonal closed pack structure, or an ABC arrangement, which is the cubic closed pack, or CCP. So ABA would mean every other layer is identical on top of each other, where ABC would mean every fourth layer would be repeated. There's a relationship between the atomic radius and the edge that can be used to determine the atomic radius of a sphere if the density of the crystal is known. If we know the radius or the edge, then we could figure out the density of the crystal. So by knowing how our atoms are arranged could help us determine what type of element makes up that arrangement. So in the simple cubic arrangement, my edge would equal 2r. In the bodied center cubic, it gets a little bit more complicated because we have to take into account the atom in the middle. So the edge would equal 4r divided by the cubed root, or the square root of 3, sorry. Face-centered cubic would actually mean that the edge is equal to the square root of 8r. So then we have some math thrown in here. When silver crystallizes, it forms a face-centered cubic. If the unit cell edge length is 408.7 picometers, calculate the density of silver. So I know that density is mass over volume. So I need to find out two pieces of information, the mass and the volume of silver when it's face-centered cubic. So knowing that it's face-centered cubic, I know that there's going to be a total of 4 atoms of silver. So I can find the mass of silver. So Avogadro's number of atoms are in 1 mole. And 1 mole of silver is 107.9 grams of silver. So that gives me a mass of 7.17 times 10 to the negative 22nd grams. So these numbers are going to be very small. Now I just have to figure out volume. Well, I know the volume of a cube is equal to length times width times height. And I know that in a cube, the edges would all be the same. So if I can find the edge, then I could just cube it. So knowing that the edge length is 408.7 picometers, then I could figure out the volume. However, when we do density, we usually don't do it in picometers, we usually do it in centimeters, so I need to convert. So 408.7 picometers, 1 picometer is 1 times 10 to the negative 12th meters, and 1 times 10 to the negative 2nd meters is 1 centimeter. So that would give me 4.087 times 10 to the negative 8 centimeters. Now I want the volume, so I would want to take my length, width, and height, which should all be the same because it's a cube, and cube it. So that gives me 6.83 times 10 to the negative 23rd centimeters cubed. So now that I have my volume and my mass, I can find my density. Because density is mass over volume. And I would have a density of 10.5 grams per centimeter cubed.